toxic yesterday.
I think it was cigarette.
It was good. Got back in the ring with some girls. It was good.
Did you touch on it?
Nope. Not as
Okay,
much.
it's probably gonna be good.
Is they not supposed to touch you, or?
I should
Well,
probably.
no, there's 20.
Nope, they got back together.
Slipped left and right. Actually, I did get 20
I
ones.
don't like it. Actually, no, I take that back. He's not a bad guy. He's just like not the type of person I would like to hang out with, and I don't understand why.
I don't know how he managed to do that.
But he himself is not a bad person.
He gotta get himself in the face with his arm, and like, he definitely knows.
If you can do that, you just do
Going okay. Yes.
I've basically been rather.
No, I think
Morning.
Get into.
I'll give him a heads up. Cutting out a few minutes early.
I was doing it.
Chant.
practice.
Chat with you. Sounds good. Yep.
Because I came to games, so I just.
Don't do it. Ignore her. Ignore her. Go through life ignoring Nicholas.
So my mom texted
I
me.
know. Why are we friends? I don't know. What is the 4 points of our friendship? Wait, what? Porpoise. What is the porpoise of our friendship? Why are we? I can hear you saying that to people actually. What is the
You know why you want to do it?
porpoise?
Because you never,
The porpoise.
ever.
Qualifications are irrelevant. What is the 4 points?
Ever.
Purpose of this conversation? I
would never, ever be. Won't you have something official so she's not your partner no more? Just for a couple of
Thank you. Dolphins always do things wrong. You spell porpoise wrong.
Ever. Don't
Okay,
ever
so
do it.
tomorrow is our great
You'll
time.
remember a lot of words.
Yeah, it'll be.
Alright, so at the beginning of the week, in the last lecture, I'm going to try to sort of link together this week's topics using a pen that works.
I think it's 26, right? Yes, I knew it. It wasn't everything. Do I do? No, it's not Tuesday. It's Wednesday. I wish it was Tuesday. I don't know where my meeting.
Alright, so on Monday, we dealt with, a review of concept of fields, and from that, developed some ideas about fluid element kinematics, right? Ideas of translation, rotation, shear, etc., and how those relate to fluid velocity fields. And then we went on to develop the differential form of the continuity equation. Today, what we're going to do is sort of continue this idea with a little more of a play on the continuity equation, which is the way we talk about conservation of mass in a field representation. And we're going to bring this idea down into what we call the stream function, which is an extremely useful way to talk about specific types of flow. And then on Friday, we're going to get into sort of the differential form of conservation of mass, or sorry, conservation of momentum. Differential momentum conservation, which takes us to the Euler equations, which are sort of one form of the equations of motion for a fluid. And then we'll be developing this eventually into, I'm sure you've heard the term before, but you may not know exactly what it means yet, that's okay. Potential flow, which, like the stream function, is a really nice way of talking about a lot of real-world flows. It's a very useful tool to have in your pocket. And then next week, we're going to be recommencing, I may have been a little ahead of myself on Monday. Next week is when we're going to get into the second half of Chapter 6 and the Navier-Stokes equations. So, to commence, first, so remember, the continuity equation, we're going to revisit this quickly to tie up a couple of loose ends. So if you recall, on Monday, the way we derived this was we said, all right, we know the control volume representation of conservation of mass, right? We could say dm dt is equal to 0, which is equal to partial t integral over control volume rho dv plus integral over control surface rho dot n dA, right? The idea is we said this term here, we can apply the divergence theorem and turn this into integral over the control volume of the gradient operator dotted with rho v dv. So now we have two control volumes inside of our expression of conservation of mass. And since they're integration over the same volume, we know that this has to hold for any choice of control volume, including, even including a point that is vanishingly small in space. And so because this holds for any choice of control volume, that means it also has to hold for what's inside of this integral here. So this allowed us to write that partial t rho plus gradient operator dotted rho v is equal to 0. All right, this is one form, or this is one way of getting to this very important equation, the continuity equation. This describes why we say that a fluid at a given point, has to conserve mass. This says a fluid in a volume has to conserve mass. This is the way we talk about it in a field. So let's quickly, though, go through another way of getting to this expression for conservation of mass, which is a little bit more visual, I suppose. So somebody stole all the pens that work, so I'm stuck with red for today. All right, so let's say we've got a fluid element here in x and y. And let's say this has length delta x, length delta y. So let me move this because that's going to get in the way. And we'll say it has a little depth delta z into the board, but I'm going to keep my drawings 2D here. So if we have flow coming in this side, right? Let's say this has a, what's the mass flux into this side? It's going to be rho u delta y delta z, right? This is the amount of mass per unit time flowing into this side of the fluid element, right? Everybody with me there? Cool. Flowing out of this side, we're assuming that rho u could be a function in space, right? This is our sort of our linear momentum per expression of our specific linear momentum, right? So out of this side, we could have coming out, it's going to be flowing across this face, which still has area delta y, delta z, but what the rate of flux and momentum across this face by a first order Taylor series expansion is what? We've been coming back to first order Taylor series expansions repeatedly. So if I have rho u here, this is delta x in width. This is going to be rho u plus quantity we're interested in is rho u. The length over which we're approximating the change in rho u, delta x, right? Is so in the x coordinate. So the slope of rho u would be represented by what? D dx rho u, right? partial x, quantity rho u. And so if that's the slope, then the change in rho u is approximated by this quantity times the distance over which it's changing, right? Linear gradient approximation, delta x. All right, let me spring this on you. Why don't you know? In the past, I've always used a delta x over 2. Why am I using just a delta x here? Exactly. Before I was saying I know the quantity here, so I had to use a first order Taylor series expansion to get it here and here. I just changed things up a little bit here by saying we know the quantity going into the element, coming out of the element. We can use a first order Taylor series expansion. Okay. So we've got the mass flux into the element and a mass flux out of the element, right? So if we look at now let's rewrite our conservation of mass in the control volume. Partial T rho P plus yes rho dA. All right, then this mass flux here it takes care of this integral, right? Because we're assuming the flows in the x direction, our only two control surfaces that we're interested in are this one, and we have rho u dot n in both of these. So on the face heading in, we draw the normals pointing out. On the face where flux is into the control volume, this rho v dot n is going to be, or the integral I should say, is going to be m dot in plus m dot out. And we end up saying that this is then equal to rho u delta y delta z, a negative sign, right, because of this v dot n at the inlet, plus rho u plus delta or d dx, rho u delta x delta y delta z. So this is our total. This is the value of our integral here then. And so plugging all of this in, what we should get is, we see here we have a rho u delta y delta z. If we distribute this out, we have a rho u delta y delta z. So we can immediately cancel that term and this entire term out, ending up with that this is in partial rho u, partial x, delta y, delta z. Alright, so that takes care of our surface integral term. Our control volume term. Well, we don't really know anything about what's going on inside of this volume. But we can say that if this vanishes to a really small point, right, would it be a fair approximation, do you think, to call this control volume simply rho times delta x, delta y, delta z? That is, they say maybe the density, kind of the average density in the control volume times the volume of the control volume. Okay, this only holds, this is only an okay thing to do if your control volume is getting really tiny. Okay, because that tells us that there isn't much of a delta x or a delta y or a delta z in which the density can vary. All right. So this is if your control volume is vanishing to a point in space, then you can go ahead and write it like this. So what we end up with now is, although you still have to keep the time derivative. So now taking this and this together, we can rewrite t rho delta x delta y delta z plus u x y z. This term here, I should generalize this a little bit. This only deals with the total change in mass flux in the x direction. If I did the same diagram in the y direction or in the z direction coming out of the board, you would get these same sort of quantities where you have partial x times rho times the velocity in the x direction. So you'd end up with plus partial y rho v partial x partial y partial z plus partial z rho w x delta y delta z. And these three terms combined can be written as gradient. Let me erase some of what we've got going on here. These three terms combined can be written as gradient dot rho u delta x delta y delta z. Now we've got this whole thing equal to 0, right? Partial t rho delta x delta y delta z is gradient dot rho u. Sorry, that's just supposed to be rho v. Delta x delta y delta z. So let's go ahead and just cancel out this delta x delta y delta z from both sides and divide it out. And what we're left with then is partial t rho plus gradient dot rho v. Same thing we had before, right? So this is two ways of getting to this expression for conservation of mass at a point in space. One way was to say, alright, we know the control volume expression for conservation of mass. Now let's change the way we express that using the divergence theorem and say that it applies to any volume, any finite size volume, including a really tiny one. And the other way was to actually figure out what the fluxes across the face of an element are and say it's shrinking in space and go through it a little bit more laboriously. But the answer we get is the same. That should give us some confidence that going about it two ways, we get the same result. It's probably something we can trust. Okay. So let's take this equation now and let's play with it a little bit, because there are some interesting things we can learn from this form of conservation of mass. If you look in your books, you probably notice that they say, oh, well, because the density is constant through a fluid, or an incompressible fluid, you can get rid of all the density terms in here, and what you end up with is just grad dot v equals 0. That is a super incorrect argument. Your book is 100% wrong in this respect. I want to be clear. That is the case for a lot of hydrolysis, people working with pipe flow and stuff. But I want to point out that as a naval architect, if you assume that rho is constant, you are in big trouble, because we're dealing with things where you have like flows that have air entrained in them, for example. Density is not constant. We're dealing with flows that may have things like, I don't know, you got like driftwood and jellyfish, things like floating around in ocean currents. Density is not constant. It's still incompressible, but you got to account for the fact that you can have stratified flows. Imagine also, ocean's really deep, temperature changes, salinity changes. There's a reason that you have warmer water at the top and colder water at the bottom. It's because the density variation across large depths of ocean water is actually great enough that it violates this assumption. Right? So whenever you see in that book where they say density is constant everywhere, send some hate mail to Bruce Munson or something, because he's poisoning your minds. But there's another way, another correct way that we can get to this form of the continuity equation. And I want to point out what that is. So, notice here, the argument of our gradient operator is not just v, it's rho, which is why we're concerned about how density varies in space and why density varies in time. Let's look at this form right here first. If we write gradient operator dot rho v, we can expand this out using the product rule, right? If we let's go ahead and say here we know rho v is equal to rho u I plus rho v j plus rho w k, and gradient operator is d dx something I plus d dy something j plus d dz something times k. Alright. So we can see that by taking the dot product, we're essentially taking partial x of this quantity here, partial y of this quantity here, partial z of this quantity here, and adding them all up. But if you're taking the derivative of a product of two terms, right? You should know this from early calc. You can write this more completely using the product rule. So for example, if we take these terms here, we're going to say that v dx rho u is equal to rho partial u partial x plus u partial rho partial x, right? This is the product rule expansion. So if we go ahead and do this for all these terms, what we get is, let's go ahead and rho partial v partial y plus v partial rho y plus rho partial z plus w. Okay, nice long expression. Let's go ahead and reorganize this. Let's take, let's take all the terms that have rows in front of them and move them over here, and then all of the terms that have rho in the actual derivative operator, move them onto this side. So what we'll end up with is a grouping that looks like this. U partial rho partial x plus v partial rho partial y plus w partial rho partial z plus rho partial u partial x plus partial v partial y plus partial w partial z. Anybody think of a more compact way to write this term right here? Partial u partial x partial v y partial w partial z. Gradient. Any special operator there? It's going to be, you're right, gradient, but no, this is a scalar expression, right? Grad dot v, exactly. Nope, it doesn't work. Grad dot v. Over here. we dealt with this in the material derivative. We had an expression that looked exactly like this. The way we wrote this was v dot grad rho. Alright? So, alright, so we have turned this expression into v dot grad rho plus rho grad dot v. By using the product rule. We're not quite done yet. You guys okay with me erasing this long scrolling mess? Okay, because if you look over here at the right, so we've done something with this term. Let's go ahead and write this term in now, additionally. What we'll get is partial t rho plus v dot grad rho plus rho grad dot v. Okay, and finally, does this expression here look familiar to anybody? You might say we have a temporal term here, a local term, and we have a convective term, right? When we write the material derivative, how do we do it? If we were to say partial rho, partial t, first term is going to be partial, and second term is going to be v dot grad rho, right? Material derivative. It's exactly what's here. Okay. And then finally, what was the way we said was the correct method to define a incompressible flow? Not that rho is constant, right? But that the density of a given particle flowing through the flow is constant. Yeah? And the material derivative gives us a way of expressing the rate of change of the density of a particle moving through the flow, does it not? This is the idea of the material derivative. We say we have a field representation of rho, we know it in space, but we want to track rho of one particle, then we apply the material derivative. And this gives us a way of saying how the density of one fluid particle changes. So if the flow is incompressible, and we say that means that each fluid particle maintains a constant density, that means that this here is identically zero. So we can cancel out this term entirely, right? Then, finally, we can say, well, alright, now since we have, that leaves us with just this term here, rho grad dot v equal to 0, we can just divide rho from both sides. We end up with grad dot v equals 0. So this is the way that we express conservation of mass when we have an incompressible fluid. And this works in steady or unsteady flow. We made no assumptions about the steadiness of the flow in getting here. We didn't cancel out any partial t's. We just showed that if we split this expression up using the product rule, what we got was one term that is the material derivative of density, which is 0 for incompressible flows. We got rid of that, and here's what we're left with. Alright, so okay. show of hands if you you understand, at least in broad strokes, the steps we took there. Get to the okay. Are there any questions about particular things we did? All right. Well, if no specific questions right now, this is an important thing to know. They explain most of it, except for this last step, pretty well in the book. But if you like, I can go ahead and I'll upload a more neatly written derivation of how we go from here to here to Canvas, so you guys can look over that and get a better idea of what the steps we took. And of course, feel free to stop by office hours. But this expression here is incredibly useful because most of the time, as fluid dynamicists, or as naval architects in particular, we're dealing with incompressible fluids. And this is a heck of a lot easier to work with than this is, because we don't have to worry about the variation of density any longer in fluid. So, let's go ahead and, it's going to take a minute to power up, run an example to see how this is a useful concept. While the screen is warming up, just a heads up, today, if I'm still jabbering when it's 15 minutes before the end of class, somebody yell at me. We have one of the engineering teaching consultants from over at the school's CRLT, or the Center for Research and Learning and Teaching. Because I am officially still a GSI, I get evaluated in the middle of the semester. So thank you all for filling out the midterm feedbacks. That's very helpful. You get to do it again, but by talking to Steve, who's sitting in the back of the room. So 15 minutes before the end of class, I'll be leaving. We'll be ending the lecture there, but he's going to come up and just sort of poll you guys on specific feedback, which he'll tell you more about, but will be made anonymous, and he doesn't know your faces, so he's not going to record whoever says they don't like me. Okay, so example. So if we're given a velocity field, remember ui plus vj is the vector velocity field, and we're given components of u and component v. Determine w. Alright? The assumption here is that the flow is incompressible, which means that we get to use this form of the continuity equation. So, let's go ahead and write these. Well, I guess step one. Who what would be a good place to start? If I just put this up in front of you and said, here's a quiz. Do it. What would be your first move, Eric? Doesn't have to be the correct first step, but you can.
So, velocity, take the velocity, gradient of velocity.
Take the gradient of the velocity, right. The terms that we do have, right? That'd be a good way of starting out. All right, so because we know that, gradient velocity is d u plus d v dy plus z equal to 0. We have u and we have v, so let's figure out the x and y derivatives of those two components. So, Christina, why don't you give me the x derivative, and Tomer the y derivative of v. Yeah.
So we're assuming that there is a W component in velocity, it's just not really.
We're assuming there's a W, but it's our job to find it,
Okay.
right? So what we're gonna get is, if I kind of give you a broad, picture of how we're doing this, we can know this, and we can know this,
Right.
and we know that there's 0, so we can solve for dWdz, and we'll integrate over c, and we'll get a W. Yeah. So. dV dy is going to be x plus z. Yes, it is. X plus z. How about du dx?
y.
d
Oh.
du dx.
I Oh, du?
Yeah, du dx.
Oh, du dx would be 2x.
All right. 2x plus x plus z plus w dz equal to 0, right? So this means that w dz is equal to negative 3x minus z, right? So if we integrate both sides of this and move over to the other side of the board, we end up with integral partial w partial z dz is equal to, I need to, is equal to integral of what was it? Negative 3x minus z minus c dz. Alright, so this tells us that w then is going to be equal to this integral. Who can I bug? Caleb, do you want to?
3xz minus z squared over 2.
3xz minus negative 3xz minus z squared over 2. But it's an indefinite integral, right? Plus, so here's the thing. It doesn't necessarily need to be a constant. It just needs to be something that's not a function of z, right? And so, in this case, we end up with plus some unknown function of x, y, and t. Okay? And that's actually as far as we can get with this problem. This is one of the things, this is one of the limitations of integrating to get velocity components, is that you only can resolve, for if you're given dw dz, for example, you can only resolve the dependence on z. If our w here, it contains a bunch of x and y and x and y and t terms, then taking dw dz is going to drop these entirely because there's no z contained inside there. So what we're able to get for the final solution then is w is equal to negative 3xz minus z squared over 2 plus some unknown function of x, y, and t. Yeah. Where's t? Well, because we never said that it's steady, right? This could be an unsteady problem. There's no unsteadiness in these terms, but there's nothing saying that there's not unsteadiness in w, right? We don't have enough information to know what that unsteady term is yet, but it could be there. So this is our, quote-unquote constant, in that there's no z dependency. Because remember, this form of incompressibility, we got rid of the time derivative, but we didn't do that by assuming that it's actually a steady flow. So this applies for every single incompressible flow, whether or not it's steady. Show of hands if you understand the process here. Alright, good deal. Alright, one more note on continuity before we move on to greener pastures. We're fluid mechanicians, budding fluid mechanicians. We like things that are round, submarines, pipes, tanks, and such. So those are all good applications of cylindrical coordinates, right? So how do we express continuity of mass in cylindrical coordinates? I think we know how to write it in vector form already, right? Colton, if I asked you to write the continuity equation, the vector form of continuity equation in cylindrical coordinates, how would we do it? You don't need to look at your notes. Remember, early in the class I said the beauty of using vector formulations, things like this, is that they're not dependent on the coordinate system you choose, right? These are valid everywhere. So these are actually still the governing equations in cylindrical coordinates, right? We still, for example, if I were, you still have, this doesn't change in cylindrical coordinates, and this itself doesn't change. The way we express this in terms of components, the way we take those derivatives, that does change. And so, for example, so there's our continuity equation. And divergence of, if we have some vector b, right, then the divergence of b in cylindrical coordinates is written like this, where you have your 1 over r, partial r, b, radial component. And then 1 over r, partial theta, b times your angular, or b, your angular component of b, and then your z component, which is still rectilinear. So in this case, b, we plug in rho v, right, is our vector component for b. And so writing this out in cylindrical coordinates, this is how we express the continuity equation expanded. Remember, so it's still written in this form if we choose to write it in vector notation, but as soon as we start actually plugging in terms or breaking it down into its radial, angular, and z components, then we need to write it out and expand it into this form here. This is written in the book. This is a pretty standard equation you can find anywhere. I don't think we need to go real in depth on how to get from, how to derive it in cylindrical coordinates. But again, I do have a derivation that I will post on Canvas if any of you want to see this, arriving at this version of the continuity equation in cylindrical coordinates from start to finish. There's a nice little write-up that somebody did that I can post for you guys to look at. Okay, so what have we gotten through today so far? That takes care of continuity. So the next thing on today's agenda is what we call the stream function. And the stream function is our first look into sort of a way of modeling flow that is actually theoretically tractable and useful for real world use. I guess if you want. Again, steady and incompressible versions of the continuity equation in cylindrical coordinates are treated, again, in vector formulation, same way as these. And if it's written out, then you just plug in your new value for grad.v or grad.rho v. Okay, but anyway, moving on now. So the stream function. There's an important subset of problems that we deal with, which we're going to refer to as this class of problems. We'll say are steady, incompressible, plane, and 2D. So we know what this means. We know what this means. We know what 2D is. And plane flow simply means that, if 2D means we need x and y components to describe the flow, plane means that there is only flow along the x and y directions. For example, if I call my domain, my 2D domain, my xy plane, if I call it this piece of paper, and I am modeling the flow of air caused by my breath, and I go, you could say that you could describe the flow in 2 dimensions, but the only velocity component is going to be normal to the paper. That is not a plane flow. All the flow in a 2D plane flow has to occur in the xy plane. So in other words, if you're saying x and y for your 2-dimensional coordinate system, then plane means you can only have u and v velocity components. W has to be 0. All right? So what's great about doing steady, incompressible plane and 2D flows is that it enables us to talk about, as I said, this thing called the stream function. So let's go ahead and write this out. We've got pens down. So written out, since we're talking about incompressible, then that means we are dealing with this version of the continuity equation. So our governing equation here is du dx plus dv dy is equal to 0, right? So let's just imagine that we can define some function. It's already written up here. We can define some function psi. This function will be made a function in x and y. All right? And we can define the velocities, u and v, as derivatives of psi. Shown here, u is partial psi, partial y, and v is partial psi, partial x. This is a little weird. Seems kind of arbitrary. But what happens now is, like looking at this, is anybody sort of getting an inkling that this might have some special meaning to our continuity equation? Let's go ahead and apply the continuity equation to these forms of the u and v velocity components. So if we say partial u, partial x is then equal to partial psi, partial squared psi, partial x, partial y, and partial v, partial y is then equal to negative partial squared psi, partial x, partial y, then partial u, partial x, plus partial v, partial y. This expression will always be 0. So what's the takeaway from this? This means that if we come up with some equation, psi, or some formula, some function in space, psi, and we define the velocity components this way, then for any choice of psi, it satisfies incompressibility. Now this is a little weird. You're saying like, what does that mean to choose a function that describes the flow? And admittedly, it's kind of an abstract concept, but we're going to play with it a little bit and show you how some of these, some of the ways in which this is useful. But the first of which is, instead of having two functions defined, u and v, right? Both of those can vary in space. You now have one function defined. And by choosing this function a special way, such that it relates u and v this way, then you guarantee that it's a physically possible, a physically admissible solution for u and v. So think of it this way. you have two unknowns, right? If you are given a problem that's in 2D space, and it's a two-dimensional velocity field, so you have u and v, both of them functions in x and y, then you have u and v are both unknowns for the problem. Your two equations then become, here's one, right? Or I should say now you, so you have one equation that relates u and v. And by imagining this function psi, we can use this to essentially reduce the number of unknowns from 2 down to 1. So now you're only searching for one thing. So, as I said, continuity is automatically satisfied by choosing a stream function. And the other cool thing about the stream function is, remember how we defined a streamline in chapter 4, I think, where we said, the streamline means that the velocity at every point on the streamline is tangential to it. And so the equation for a streamline was written this way, where we said that the v over u is equal to the slope of the streamline, right? Well, if we take this definition of psi here and plug in v over u, no, sorry, let's do it a different way. There's a nicer way of coming up with this. All right. So let's imagine that we have two streamlines in space, okay, or 2 points in space, and we want to calculate. Let's say we have a point along one streamline and a point along another, and that ends. Grab it out of them too. Okay, let's imagine we've got point 1, point 2. They're different points in space, and they're on different streamlines. Then we can say that the change in psi, right, between these 2 points in space can be written as partial psi, partial x, times delta x plus partial psi, partial y, plus delta y. That is the path between these. You have psi 1, you have psi 2, partial x, partial y. Does this make sense? The way we're just approximating the change in the stream function from point 1 to point 2 by breaking it up into derivatives in x and y and multiplying by the distance in x and y. All right. So if we take this term and replace them with what are in these components here, we can see that now partial psi ends up being negative v partial x plus u partial y. All right, so now let's go ahead and say, all right, well, what if we're interested in the case where the streamline, or where the stream function doesn't change at all? Okay, what if we want to say arbitrarily that delta psi is equal to 0? What this gives us then is x plus u delta y. Let's go ahead and move this v delta x over onto this side of the equation, so we end up with v delta x is equal to u delta y, which leads us to v over u is equal to delta y over delta x, which, as we say delta x and delta y get very small, turns into partial y, partial x. So this is what happens when there's no change in the stream function. So when stream function is equal to a constant, you get velocities and derivatives in space related this way, which are exactly identical to the way we define a streamline. So the takeaway here, this is big, and this is why the stream function is even called the stream function, is that the stream function is constant along a streamline. If you say, I have a function psi, and you say set psi equal to a constant number, and you plot all of the x and y values that keep that psi at a constant number, what you get is a streamline. So it is not only useful as a way of satisfying continuity, but it gives us a way of visualizing streamlines in a flow. There's another neat little trick we can pull with the stream function that's related to this as well. So let's say I use this same analogy. I have two streamlines. Okay? I have two streamlines. One of them has a constant psi1, one of them is a constant psi2. Now let's say I define this point here as A, this point as B, and we'll put a line between them that's alright. So I put a line between A and B. That is a line across these two streamlines. And the question I'm going to ask now is let me black this out for a minute. I feel like that's getting distracting. Alright, and the question I'm going to ask now is what is the flow rate across this line between A and B? Okay? So, what is the volumetric flow rate? Q dot AB. So the way we might solve this is by saying, alright, well, flow across, we'll define this corner here as C. Flow across QAB, well, I guess we don't need a dot, do we? QAB is equal to flow across this boundary plus flow across this boundary, right? So we can say QBC plus QCA, right? Flow across QBC now could be described by the horizontal velocity, this point, times the width of this line segment BC. So, in other words, QBC is going to be equal to U delta Y, right? Here, let's make this a little more general. Really, if we're treating this sort of as a control surface problem, integral from C to B of U Y, which equals integral from C to B Y of, let's say, U is equal to let's go ahead and plug this value in for U. We end up with gamma partial Y to dy. So what we end up getting then is that this sort of turns into just an integral from integral from C to B partial psi, which means we get psi B minus psi C. Now, QCA, we go through a similar process. We can say that QCA is equal to the integral from, well, we'll say AC. Sorry. QAC is equal to the integral from A to C of V dx. Drawn this way, we can see that V is going to be it's going to be in the negative direction, right? So we end up with negative v dx, which turns into integral from a to c, plugging in v here. Special x dx. We've got two negative signs, one from here and one from the fact that v is in the negative direction, so those cancel out. And so what this ends up giving us is now psi a minus psi, this is supposed to be integral from a to c. Yes. Alright, psi c minus psi a. So c minus psi a. So we can cancel these components out because we have a minus and a plus, and we get that the flow rate between A and B is equal to gamma B, or psi B minus psi A. Right? So that's psi at these 2 points. And psi A here is just equal to psi 1. And psi B is equal to psi 2 because psi is constant on each of these streamlines. So this gives us psi 2 minus psi 1. What does this mean? This means that for any two streamlines, right, the flow between those streamlines is equal to, the volumetric flow rate between those streamlines is equal to the difference in the stream function. Why is this good? Why is this important? Remember, flow doesn't cross streamlines. That's the definition of a streamline. It only goes along streamlines. And so there's, you know, kind of in an abstract sense, streamlines behave sort of like walls. So you could just as easily, if you assumed inviscid flow, you could say, well, these streamlines aren't streamlines, and now they're walls of a pipe. Okay? And now, by just looking at the values of the stream functions at the edge of the pipe, you can calculate the flow rate through a two-dimensional slice of that pipe. Yeah?
Does that mean the units for the stream function are length cubed per time?
Well, let's look at that. That's a good question. So we've got here that, like, units here, or dimensions, I guess. We have length per time, length over time is equal to question mark over length, right? So that means that our the units of the stream function have to be equal to length squared per time, right? So in this case it would be something like meters squared per second.
So then how can it be that that you know the difference is the volumetric flow rate?
Because it's a 2D flow. So I guess yeah, volumetric may be a misnomer. It's more the area flow rate. Thing is, so this has been presented for 2D flow. There's also a version of the stream function that's in 3D, but it's a huge pain actually, because you end up you don't get a stream function, you get a stream function vector, and so you end up having 3 stream functions, which then satisfy continuity. And I guess there are certain situations in which it actually makes the problem easier, but I have never seen one. So you might end up getting into 3-dimensional stream functions with Bernitzes when you take 321, because it is a good thing to know. It's a useful idea, but most people start using potential flow once you get into stream functions, and once you start getting into 3D flows, because potential flow allows you to do the same sort of stuff, but it's not as complicated once beyond 2D flow. All right, so this is a good fact. This is a good thing to know. Flow rate is equal to the change in the stream function. All right, and again, let's see. So let's say that we'll call this QAB is equal to big delta psi 2 minus psi 1. If delta psi here is greater than 0, anyone know what that's going to imply? about the direction of the flow. Well, the way I did this derivation, right, I sort of assumed that the flow was heading in this direction. Yeah? I kind of did everything under the assumption that the flow is heading through the pipe this way, as it's flowing across this boundary, downward, this boundary to the right, and what I got was this expression, this, so positive, a positive delta psi, that is if psi 2 is greater than psi 1, that means the flow is going to be to the right, okay? If psi 1 is greater than psi 2, and delta psi is equal to, or is less than 1, then it's sort of as if I did this derivation with all of the signs on my integrals flipped. Okay, that means that the flow is heading up. So as a rule of thumb, if you look at two streamlines, let's see, how can we approximate this? If you look at two streamlines, I think you could use a sort of a right-hand rule here. You put your fist on the streamline with the higher value of psi, point towards the streamline lower value of psi, and then the next axis is going to be pointing in the direction of flow, right? So if you put your fist, higher streamline, index finger pointing in the direction of the decreasing stream function, then flow is going to be in the direction of your middle finger. Okay, this too, oh, that looks like that's, we're at quarter till. So we got halfway through stream function stuff. So I guess on Friday we'll wrap up with one example on stream functions, showing how you can use it to plot velocity fields and velocity at streamlines very easily. And then we'll get through as much stuff as we can here and make up the remainder next week. So with that, I will turn over the floor to Stephen, the ETC.
Great, yeah, thank you guys for sticking around and doing this. Like Casey said, my name is Steve. I'm an engineering teaching consultant. I'm also a PhD student here at Michigan in computer science. And I work for CRLT, Center for Research and Learning and Teaching, the engineering division. And we offer a bunch of different services to help out GSIs and IAs here at the university. And so one of the things we do is called midterm student feedback, or MSF. Has anyone participated in MSF before? Alright, so it'll be new for everyone. It's pretty easy. So the difference between this and the online forms you fill out is that this feedback is just going to be for Casey's benefit. So it's not shared with instructors or administrators or anything like that. It's just something to collect some